Hi, Ulysses here, back with another Ask Our Experts episode about clocks and timing. Today, Sieg will describe some of the other parameters that engineers use to determine whether a clock is a good fit for a given application. Sieg, what are some other important timing parameters we need to take into account?
So there are several other important clock parameters that may be a little easier to understand than the ones I've talked about so far. But one thing to realize here is that I've had an implicit assumption through all these previous videos. And that implicit assumption is that the event occurs instantaneously. Another way of saying that is that the clock rising edge takes zero amount of time. Now, of course, in the real world, that doesn't happen. A clock edge will have a certain rising time and a certain falling time. So, since we are focused on the clock rising edge for the purposes of this discussion, we'll talk about the rising edge. So, a clock rise time is often specified between some percentages of the amplitude. Typically, we will see a clock edge defined between a 20 and 80% level of the clock's amplitude. Perhaps we will see it defined between a 10 and 90% level of the clock's amplitude. We can determine whether this edge is too fast or too slow for a given application. Now, another way that we can discuss how fast a clock rising edge is by using a term we call slew rate. So the way we determine slew rate is we take the slope of the clock edge between, say, 20 and 80%. So let's use an example of a 3.3 volt clock, and we want to know the slew rate of its rising edge. Let's keep the number simple. So let's say we have a 20% level of 3.3 volts, which is 0.65 volts. We have an 80% level of 3.3 volts, which is 2.65 volts. So that is an amplitude of 2 volts. If you remember your high school math, rise over run, the rise is 2 volts, and this occurs in a time of, let's say, 1 nanosecond. So the slew rate of this clock is 2 volts per nanosecond. And in fact, volts per nanosecond is probably the most common way that you will see slew rate expressed in clocks. Now, slew rate or rise time, they can vary depending on the format of the output driver, the device that is creating this rising edge. It could be a CMOS output, it could be an LVDS output, it could be an HCSL output, it could be an LVPECL output, and the list goes on. And so typically in electronic systems, we will see clock rise times that range anywhere from 100 picoseconds all the way up to a few nanoseconds. Another parameter that can determine whether a clock is good enough for a specific application is the duty cycle. Now, the duty cycle is simply the percentage of the period where the clock is high. So if we have a 1 Hertz clock with a period of 1 second and the clock stays high for 600 milliseconds, then it is high 60% of the period, and we call that a 60% duty cycle. Now, typically, we will see oscillators that are specified to have a duty cycle in the range of, say, 45 to 55%. Sometimes you will see the duty cycle specified from 40% to 60%. And in some really high performance cases, you may see the duty cycle specified from 48% to 52%. All right, so let's move on from duty cycle to something we call propagation delay or input-output delay. This is often abbreviated as I/O delay. Let's say I have a 1 megahertz clock and it is coming into a buffer and it's coming out on the other side of that buffer. Of course, it's going to be another 1 megahertz clock. The rising edge of that incoming 1 megahertz clock goes through the buffer and produces the rising edge on the output. Now, of course, this rising edge of the output does not happen at exactly the same time as the rising edge hit the input of the buffer. That's the propagation delay. That's the I/O delay. So, for example, it may take 1 nanosecond for this clock to propagate through the buffer. All right, that's I/O delay. I/O delay is really a subset of the parameter we call skew, which is the last parameter that we're going to be discussing now. Let's take this buffer, and instead of having one output, let's say it has 3 or 4 outputs. So let's say we have this rising edge that comes in, and output 1 of the buffer has that rising edge come out at 1.1 nanoseconds later. And let's say that output 3 of that buffer has the output arriving 1.3 nanoseconds later. So the clocks have come out at a different time. That is the skew. The difference between when those clocks came out is the skew. In this case, the skew was the difference between 1.1 nanoseconds and 1.3 nanoseconds, which is 200 picoseconds. Typically, you will see skews in the range of 50 picoseconds, and sometimes they can go all the way up in the range of 100 or 200 picoseconds for an integrated circuit.
Thanks, Sieg, and thank you for watching all the videos in this clock and timing series. Also, make sure to check out our links in the description below for more information on clocks and timing. And as always, don't forget to subscribe to our YouTube channel to be the first to know when we have more insights from our experts. See you in our next series.